here. Can I have my slides, please? Okay. So today, the title of my talk was about, I wanted to talk about a new way of analyzing functional MRI, but the symposium organizer looked at the things that I had done and decided that it's, and changed the title to Revolutionizing Functional MRI. I'm very humbled and flattered, but we are very far from revolutionizing fMRI. But here I'm going to talk about a couple of things that basically do to improve what we have and making a step forward. So let's talk about what we mean when we are talking about functional MRI. Probably you all know that with MRI machines, we can create great anatomical image of the brain and other organs of, in the body. And from this anatomical image, we can infer some physiological information. So for example, if we look at the image of the brain of a subject and the temporal lobe is missing, we can conclude that subjects would have some memory problems. But with functional imaging, we wanted to go one step ahead and image the function of the brain directly. And by doing so, we can identify the area of the brain that are responsible for a specific task. But we can also go further and see what happens inside the brain when we are not doing any specific task. Because when we are at rest, there's still a lot going on in our brain, and different parts of the brain are talking to each other and connected with each other. And with this specific category of functional MRI, which is called resting state functional MRI, we try to identify these networks in the brain at rest. To basically identify these networks, we look at the fMRI signal from one area of the brain that we are interested in, and then compare this time course or this signal that we are getting with signals from other areas of the brain and identify the ones that basically follow the same pattern. These areas that basically have the same pattern are called functional connectivity networks, and this is what we measure with resting state functional MRI. And these functional connectivity networks, there are many of them. One of the most famous one is default mode network, as you can see here. And default mode network is shown to be a very important network in the function of the brain, and it is implicated in many neurological diseases. For example, it has been shown to be affected in Alzheimer's disease, and because of that, it could be used as a biomarker or as a tool to detect the Alzheimer's disease at early stage of the disease. It's very important because in case of Alzheimer's disease, the disease has a very long preclinical stage for 10 to 20 years, during which the patient doesn't have any symptoms. So with traditional symptomatic diagnosis, you cannot identify those subjects. So we need to rely on some tools, for example, the medical imaging tools, to identify those subjects. And resting state fMRI is a good candidate because it can the data can be easily collected. There's no radiation or exposure involved. You can repeat the test as much as you want. And patients can be evaluated because they don't need to perform any specific task. The problem is that currently, the maps that we are getting are not reliably interpretable at the single subject level. And the reason is that the data that we are getting is very noisy and doesn't have a good contrast-to-noise ratio. And because of that, when we combine the data from many subjects, it's very useful. It gives us a lot of useful information. But for clinical use, to be able to use it at the single subject level for one single patient, we need much improvement in the quality of the maps that we are getting. So how to improve that, and basically how to revolutionize functional MRI. Basically, we have been trying to improve every aspect of functional MRI imaging, including acquisition, trying to get better data, improving the pre-processing and denoising the data and cleaning it up more effectively, and finally processing. And here I'm going to talk about the way that we are collecting functional MRI typically takes more than 2 seconds to just have one measurement. But with the ultra-fast fMRI, we can basically image many slices at the same time, and by doing so, we can improve the resolution, the time resolution between these acquisitions significantly. So, for example, in our lab, we could reduce the time required to image one volume of the brain to 350 milliseconds. So first of all, it gives us a lot of samples, so by itself, it improves the quality of the images, but it also has some other advantages, particularly in terms of improving the way that we are denoising the data. Because fMRI data is a very noisy data. We have signal, which is basically the change in the MRI signal related to neural activity, but also we have other unrelated changes, mainly the changes that are related to physiological phenomena going on in the brain, particularly respiration and cardiac cycles would change. And traditionally, when the temporal resolution is not very good, this signal gets mixed with those noise, and it's very hard to remove them from the data. But with this ultra-fast fMRI, you can basically filter them in the frequency domain. In the left, we have the data from the conventional way, and on right, you see the data from the optimized version, and as you can see, it very much faster gives us a very clean, less noisy results and maps. So because of this improved pre-processing, we can basically measure these functional connectivity networks much faster from shorter periods of time. And by doing so, it basically improved the sensitivity and reliability of our measurements. And both of them are very important when we wanted to use it at the single subject level as a clinical tool. So now that we are able to measure the functional connectivity networks from shorter periods of time, we can also change the way that we are processing the data. So traditionally, we scan the subjects for about 10 minutes, and out of that 10 minutes, the output is just one stationary map of, for example, default network here. So basically, the assumption behind it is that the functional connectivity networks doesn't change over time, where in fact, from electrophysiological studies, we know that it's not true. And this network is very dynamic, and it changes significantly over the duration of the scan. And there is a lot of information here that has been neglected so far. It's like a difference between looking at a picture and looking at the movie. There's a lot of information that can be useful and improve our sensitivity and reliability that has been neglected so far. So another thing that we started working on was trying to find ways to extract more information by dynamically analyzing the data. So one thing that we can do is that instead of analyzing the whole data, we can analyze the data over shorter periods of time and put those maps next to each other and basically have a better understanding of how these networks changes over time. And when we put these maps that has been measured over shorter periods of time, here they have been measured over 17 seconds of the data rather than 10 minutes. Now we can extract some dynamic information. One thing that we can do is, for example, get these individual maps and using machine learning and clustering techniques, divide them into different states. So basically, we assume that during the scan time, the brain switch between different states, and that's how we characterize the dynamics of the system. And if we look at different subjects, we can see how they do the transition between different states. And if we extract some information from these transition maps, we can basically differentiate between Alzheimer's disease patients and healthy subjects. And for example, in this study, we identified that the time spent in this state would be a good classifier for Alzheimer's disease versus healthy subjects. And also here is another way that we have been trying to extract the dynamic features of functional connectivity. So here I'm going to explain how this model works. It's called DCC Garch model. And if you look at these four plots here, these are basically the time series or fMRI signal that we are getting from resting state fMRI studies. And if you look at these four, you basically cannot see any significant difference between them. They all look the same. If we look at the stationary functional connectivity between them, again, in terms of like stationary connectivity, they are pretty much the same. You cannot differentiate them. But if you look at the way that the correlation between the time series change over time, you see that they have very, very distinct and different patterns. Here they change a lot. They have fast changes happening in the correlation, but overall it doesn't change. Here we have variations. Here it's pretty much constant, and here it's changing rapidly. So these four dynamic patterns is something that now, using this method, we can model. And so, for example, this model have two parameters that using them, we can basically characterize each of these methods. So we use that again for developing biomarkers for Alzheimer's disease. We looked at the default mode network and extract the time courses, and then model the dynamic correlation between these time courses using the DCC Garch model. And this is the results that we got. So for example, and we compared it with stationary traditional functional connectivity measures. With the stationary functional connectivity measures, we didn't see any significant difference between Alzheimer's disease and control ones, but with the dynamic DCC Garch models, we were able to see significant difference between them. And the interesting thing about this study was that we completely ignored the symptoms and basically divided the subjects into A beta positive and A beta negative purely based on the pathological changes that is happening in the brain and not the symptoms. And because of that, we were able to identify some patients which were at very early stage, during which they don't have any memory problem, they don't have any cognitive problem, but we were able to detect some of these pathological changes that is happening in the brain. So that's very encouraging and important. So hopefully today I showed that by improving the acquisition, pre-processing, and processing of resting state fMRI data, we can increase the sensitivity of resting state functional connectivity measurements, and by doing that, get closer to have biomarkers for different neurological diseases, particularly Alzheimer's disease that we are interested in. And we showed that by comparing it with stationary functional connectivity measures, we have a huge boost in sensitivity and also in reliability of this method. And in fact, this approach is what we are using here in a collaborative work with Dr. Halsworth and Dr. Fernandez, and we're going to basically use the same approach and the same techniques for ADHD patients here at Matai Institute. So, and the initial results that we got from this approach was very promising, and this is a very exciting line of research that we are pursuing here. And with that, I would like to thank my collaborators at University of Washington, and also Dr. Hernandez and Halsworth and Matai Institute for inviting me here. It was a great pleasure and privilege to be here and talk to you about the works that we have been doing. I really appreciate it, and also the funding agencies that has funded this research. And I would also like to take this opportunity and congratulate Puti Keteteke for being elected as the bird of the century. I apologize for interfering in your election, but you know, Americans, they cannot help it. When there's an election, they would like to interfere somehow. And with that, I'm going to conclude. Thank you very much. I appreciate it.